Why am I fake? He wants to learn Fenwick tree. I would just tell them that you don't need to know Fenwick tree. Standard segment trees are enough, and you need to learn them anyway. And also mute. Yeah, this is muted. Great. Rank transform of a matrix. Did we have some team? Okay. Oh, because I'm not signed in. Makes sense. Here we go. Everything is visible. Thoughts on CodeChef? It's fine. You can solve problems from CodeChef. Right. Rank transform of a matrix. This was one of problems that I gave you as a homework around 2 weeks ago. At least in Discord, I posted links with those problems. And this is the third of them. This is the one I didn't manage to do in time last week, just because the other two took a lot of time. Given a matrix, return a new matrix where in every cell you put rank of this cell. Rank is an integer that represents how large an element is compared to other elements, and there are some rules. If two elements are in the same row or column, then rank needs to be smaller if the value is smaller. The closest term to this that you might already have encountered is called coordinate compression. And this is two-dimensional version of coordinate compression, where not only we do it for an array, but actually we'll do it for 2 dimensions. Maybe I should have named my stream differently. This will be kind of a lecture about coordinate compression. Maybe I should go full screen. Yeah. You will see more. Right, how this looks like for a single array. For a single array, sometimes you need to use values as indices in an array. Almost always you can use a hash map for that, and let's see an example of this. There is an array, say with values 5, 10, 12, 200, 7, and 10 again. And you want to answer queries. Where is number 200? And you want to say, oh, 200 is at index 3. Where is number 5? 5 is at index 0. Where is number 10? 10 is at index 1, and if you want to keep all occurrences, then it's also at index 5. 7 at index 4, and so on. You can keep all of this in a map. Or if you want to make it fast, in C++, that would be an ordered map, or a hash map, dictionary. It's called index compression in CP handbook. I think the coordinate compression is more common name, but I can write this down as well. I wonder how is the font. I see it on my phone, so I think it's no. How much do you hear my fan in a laptop? Is there a constant noise? But I think the video is clear. Hi Alejandro. I think even if I stream not from my room, I need to grab a second monitor. Great, no noise. I hear a noise, but apparently the microphone is good at cancelling the noise from the same laptop. Okay, what are disadvantages of a map or an ordered map? They are slow. Even with an ordered map, or just in general hash map, it is, I would say, 5 times slower than an array, maybe even more slower. And it doesn't have the same functionalities like find the next value or something like that. So you don't know. If I asked you about now lower bound on value, say 30, so that's the next value after 30 that is present in this array, or in other words, I want to get something as small as possible but greater than 30, give me this value and its index. You couldn't use an ordered map for that. You could use a map, because then it's ordered. You can use lower bound, but then it's logarithmic and very slow because of a map. So we don't like that. We generally do coordinate compression to we do it to avoid maps. And we do one mapping, so forever now we would know what every number actually represents. One way of thinking about it is if we kept this in a map, then just where every number would be. So in other words, we want this sorted. And let's say we remove repetitions. There is an array 5, 7, 12, 10, 12, 200. That's a sorted version of the same array, if I didn't skip a number. But even more, I want to say that I can kind of replace it with indices. The order will be preserved. And now I can apply the same indices to the initial array. And that's 0, 10 is 2, 12 is 3, 200 is 4. I'm just reading from this mapping below. Or also I could do it from this mapping. So just wait, something is off. I still at position 5 here. Oh, because that was in unsorted array. Never mind. Am I out of home? Yes. That's right, not the usual set. 7 is at position 1, and 10 is again at position 2. Now, this new array, 0, 2, 3, 4, 1, 2, is the compressed array, like this one, where the order of numbers is preserved. Still, at the first position, we have the smallest value. Still, here was 10, and there are two smaller values, 5, 7, and there is here a smaller value too. So we mapped now not from value to index, but from value to the smaller occurrence of the same value. Not smaller occurrence, smaller version. Maybe maybe easier to understand example is if we do the same with characters. The most common way of mapping characters is, let's say like this. If you have A, C, D, Z, A, you can change it to 1, 3, 4, 26, 1. Every character you can change to the ID of alphabet, ID in the alphabet of this character. But we can be more efficient. We don't want this 26 because now this sequence is very ugly. We just care for every two characters which of them is greater. So I can kind of compress that and say, no, I don't want to use 26. I will just use values up to 4. This sequence describes the string in the same way as the previous sequence, if we don't care about exact values, but only about comparison. We see that here is the biggest value, 3 is the second biggest, and so on. 1 is the smallest. So at the first position and the last position, there is smallest value, because it was A in the string. So I said that we do it mainly to avoid maps, but in competitive programming, we do it almost always to use segment trees. It's extremely common there, because when you build segment tree, you build it over some sequence of limited size. You cannot build a segment tree over size 1 billion, at least not the trivial segment tree. And the link will not work, sorry about that. Somebody can copy paste the link. But of course, in LeetCode, we don't care about this reason. We care about this one and the speed. So this problem, in a very artificial way, and maybe not that artificial, it forces us to use coordinate compression. And actually, while we usually use coordinate compression in order to get a sequence where later some queries will be possible to be done easier, in this case, we just want output of this coordinate compression step. But we will do it in 2D. In one dimension, so also if this matrix was of height 1, if n was equal to 1, then we would get just an array. Input is array. And this is that standard thing that you should already know. Well, link to the problem. Let me give you from time to time I can copy paste. for what do we do for an array? Uh, we can use a map, but when possible, we want to avoid the map because it's slow. Or instead, we can use sorting. We can sort those values. But if I just sort them, and then I get 5, 7, 10, 12, actually 10 again, 12, 200, this is maybe not that helpful. This is the input array. This is sorted version of the same array. How does this sorted version, I will remove everything else. How does this sorted version help in getting the compressed array? We know here that 5 is at position 0, 7 at position 1, 10, there is a repetition, we want to get rid of it, to just say that 10 is between 7 and 12. So we now know a mapping, 0, 1, 2, 3, 4. And with mapping, we can use a map. Let's see first, not the most efficient, but still a valid way to use coordinate compression. You grab a sequence, let's say that we are given a sequence A, and we need to return compressed version of this sequence. Then we copy A into, let's say, sequence S, we sort it, then we remove repetitions. How do we remove repetitions though? We can iterate through it and always compare a number to a neighbor, or we can use some function for that, and there is a function unique in C++. But it's very inconvenient to use it still. This is such an ugly one-liner. You need to be able to remove repetitions from a sorted sequence. Even if you are aware of this function, you should know how to do it just with some for loop and grabbing elements one by one if they are actually the first out of new block of numbers. Remove repetitions. Now we can create a map or a hash map if you prefer. Let's save that as mapping. Iterate over this sorted sequence and remember the mapping. Like in the example below, that would mean knowing from 5 we should get 0, 7 is transformed to 1, 10 to 2, and so on. This kind of mapping. Then we can go through the initial sequence, use the mapping on initial sequence. A size A of I is mapping of A of I. And return A if needed. Hi Limagbar. New background looks nice. Don't get used to it. That's not. This is a one-time thing, but I'm happy you like the background. This is for remove repetitions. This line removes repetitions. We copy the sequence A into a new one, S. We sort the sequence S. We remove repetitions from S. So like, let's go with an example. That A is initially, let's say, this. Once we sort it, we get a repeated 10. Repeated 10. Then we remove repetitions, so hopefully we get this without additional 10. And then we store the mapping like 5 goes to 0, 7 goes to 1, and so on. We use the mapping now, and so we apply this mapping to the initial sequence. We should get exactly this. So 0, 2, 3, 4, 1. Here you go. I'm looking at the chat to see questions. Can you use set for removing repetitions? Yes, you can. You can. In terms of this part, set is a bit too powerful to be used for removing repetitions. If you care about efficiency of your code, not the time complexity, just running time, then sets should be avoided, but in interviews it doesn't matter. So yeah, this part I marked can be replaced with a set. But also it can be done by sorting a vector and then doing a for loop or using a function, proper function for this in your language. Actually, I will replace this with a set. I think it's indeed quite convenient. Set of int from a begin to a end. I think this works. This is a constructor for a set, so I inserted everything from A into S. Repetitions get removed automatically. And now I want to iterate over this set for every element in set. Mapping of this element becomes I. But what is I? I is initially 0. And here we do I++. Mapping of first element will be 0, then 1, and so on. But then I cannot reuse I. Let me change the name here to next available index. Here you go. Now we did the same with a set. Store the frequency of every element. Do we need the frequency? I think you don't need frequency, you need just all occurrences. That's something more than just frequency. It isn't enough to know that element 100 appears 3 times. You need to know where it appears. Lower bound is ideal. We will use lower bound indeed. Set of int s of this also works. Okay, I will improve. Thank you. Here we go. This is a version with a map and a set. That's double inefficient. I guarantee you that we can do like 5 times faster in practice. Not that it's important, because it doesn't improve their time complexity. This is n log n, and at the end we will still have n log n. By the way, we for sure need that, maybe not for sure, it is not obvious. Yeah, it is. You cannot solve this problem faster than n log n because you cannot sort numbers faster than n log n. Let's say it like that. And if you were able to do mapping very fast, then you would use now this mapping to values from 0 to n minus 1 to actually sort in linear time, because numbers from 0 to n minus 1 you can sort in linear time. DP for each cell? No, because when you look only at top left cell, you will not figure out its rank. This is not DP problem, because to know what value to put at top left, you actually need to know a lot about other values. If anything, it's more like BFS than DP. But it's a very strange way to think about it. Later, after I present you a nice solution, I will talk about graph interpretation and about BFS. You will invent linear sorting algorithm? I can take some bet for it. Erratic sort is O of n. This is why I'm saying that if you are actually able to get mapping into this compressed version, then you're able to sort in linear time, right? Because then the values are compressed. So erratic isn't O of n, it's O of value of a number. Let's now avoid set and map, but it's only a fancier way, something without heavy data structures. Maybe also the advantage is that you can use it in any language. I will sort numbers first. So I will get back. I will remove now the examples. They are not very important here. So what do? We copy, put this SSA, and we sort. That doesn't change. We remove repetitions. I should have not removed it. As resize, unique as begin, as end. This is that previous code I had for removing repetitions. But now I will not do a mapping in some kind of a map, but instead I will say AI is, and here I will figure out what index it should get. And I will use for this a sorted sequence. Because if the sorted sequence here is like this, and now I know that AI is equal to 12, how do I find the index of 12 quickly? Tell me, chat, this is not a tricky question, and somebody already earlier mentioned what do we use for that. What do we use in sorted sequence to get index of a number? It's proven that you cannot sort faster than n log n if you only use comparisons. But if you can use other things, then well, that's a different story. Array index of 12. No, that's bad. If you, but binary search, I agree. So binary search is a good answer. Remember when you run something like this, get index, I don't know what you have in your languages. Most of the time, this is linear. Don't assume that if you type one function, one operation, it is constant. To get index of a value in a general array, it is linear because it needs to iterate through the whole array. It's not that index or general get index function knows that the sequence is sorted. Unless in your language this function is logarithmic and it assumes that the array is sorted. But I can bet that this is linear in like Java or Python. I don't think C++ has index function. Is unique quadratic? No. Unique is linear. Here we use, I think, lower bound. I wonder if we can do some kind of find. Find is linear, so we need lower bound. But I will first do it with, let's say, pseudocode. Find with binary search, AI, in value AI, in sorted sequence S. So where in this sequence there is value AI. But actually this is how you do it, lower bound. It also is able to find greater number, but we know that this exact number exists. In sequence S, we are looking for AI. And this will give you, I believe, a pointer, and you need to subtract to get the index. Now done. Use binary search for the last step, and this is the code. This is standard coordinate compression or index compression. Here you go. Do you have questions about this thing? Lower bound finds in this array, it finds this number or greater. But we know that this number exists, so it will find position of this number. Ideal 100 out of 100. Thank you, thank you. Unique returns number of different numbers in an array. I don't know if that's a question to you because you add somebody else. It removes duplicates and gives you a pointer to a new end of array after all the unique elements. You need to combine it with resize to make it work, to really get rid of those old elements on the right. Right now we didn't, so far we didn't talk about a matrix. It was for one dimension. Now it's time to move to 2 dimensions. Now time to move to 2D. And that should be quite obvious for you whenever you solve a problem. If it's in 2 dimensions and you cannot solve it, first think about 1 dimension, and then recognize either that it's a well-known problem or just figure out a solution. In 1 dimension, it can only be easier than in 2 dimensions. Maybe with some very few exceptions. And like it's a square. You have a template for unique. That's fine. I use this thing. Now it's 2 dimensions. And it will not work that well to just grab everything from the matrix, sort it, and then assign values like this. Let's see a counterexample to that. Let's say that I do exactly that. I think it will not work for 10, 20, 30, 40. Right? Yep. It will not work here. This naive version of compressing coordinates. If I grab all the values, so 10, 20, 30, 40, I map them into indices. That's 0, 1, 2, 3. And now I change them according to those indices. Actually, I need to use values from 1 to n. So 1, 2, 3, 4. Let's say it's like this. It will not work. This is example, exactly same as example 1 here, just I multiplied all the values by 10, not to confuse it with indices. I do recommend this when you want to deal with values, but also with indices heavily in a problem. As your values in an example, use something that will not be mistaken with indices. When you look at this 1, 2, 3, 4, and it gets transformed to 1, 2, 2, 3, it's not that when you see one of those matrices, you will immediately know which one it is. With my input matrix like that, we know that this is input matrix. Picture looks cool. You mean this picture on the right? Some nature on the wall. Right. What now? By the way, there is a storm outside and heavy rain. So in case the stream is suddenly over, most likely I lost the power. How much did I pay? Nothing. I'm in my hometown, so that's my family's house. I didn't arrange the background. Also, it's I'm sure it's cheap. It's not real painting or anything like that. Just something you can use instead of paint on your wall. This shows why if we just map like this, we would get 1, 2, 3, 4, but we need to, the conditions are a bit more complicated. We don't care about comparison of two values if they are not in the same row or the same column. How do we binary search the matrix for each cell? Well, this wrong approach I suggested, it's just applying this previous algorithm. That is, grab all the values from the matrix, sort them and remove repetitions, and then for each cell in the matrix, replace this value with a lower bounded index. You can use with binary search the index in sorted sequence. But that doesn't work because the conditions here talk only about satisfying inequalities between two cells in the same row or the same column. Chat, tell me ideas. It would be best if I hear now some incorrect ideas as well. What do we do? Constraints are up to 500. I think in code forces it would mean that cubic solution is fine, but this is LeetCode, so squared solution is fine. This is a cancer problem. I'm sorry about it. You also need to solve cancer problems if you want to get good. Sort all the values, keep track of given compressed ID, new ID to this, from I or column J. That's something. I like the suggestion by QG, so let's go with this one. Let me copy paste this. I will drop the nickname, but still, QG, that's your idea. You can feel happy or ashamed once we realize if it's good or not. Sort all the values, keep track of given compressed ID. Maybe I will drop this line. Give the new ID of, so change array of ij to max ID from row I and column j. That makes a lot of sense. So if you have some kind of matrix and you look at every cell, let's say we look at this cell here. We want to look at this row and we want to look at this column kind of separately. From both of those, we would get some kind of condition that this number needs to be at least x. In particular, let's say that there were some too small values here, and I changed them to 1 and 2. There is here some huge value. It is infinity for now. We didn't assign it yet. So from this, it seems that x, if it was initially greater than those two elements, then this should be free. We also look at the column. Maybe in column we have here a very small element, we change it to 1. Here there is infinity, we didn't yet fix this element. So from this we would get that x is 2. And now we say that x is maximum out of 2 and 3, out of ID that seems to be required by a column and by a row. I hope that I understood QG correctly. This is some interpretation. This is a straightforward idea from the statement. In every row and every column, we need to satisfy inequalities. So, like in every row, kind of, you want to do coordinate compression separately, but also it needs to happen at the same time in columns. So for every cell, it should be greater than everything else that is smaller initially in the same row or column. In particular, we want to minimize ranks. So if we know that in the same row there is 1 and 2, in the same column is 1, it's not that x we want it to be 5, but we will minimize it. It will be 3. So it's we look at maximum from row, from column, we choose the one that requires more of us. Like this says x needs to be at least 3. So we go with 3. In this case, x is 3. But here's the thing. If I do it like this, it will not work. Now, chat, you tell me why. For every I, from 0 to n minus 1, or n minus 1, for every j, array of ij is, and here we apply the algorithm that we came up with. First thing is that this is currently, most likely, too slow, but we can deal with that. There are data structures that will quickly tell us this, even not data structures. For every row and column, we can keep next number that is available. How do we construct? From where do we start? That's a good question, and there follows a good answer. Sort all elements. When I give you a huge array, maybe huge matrix like this one, this thing, what do we know in this matrix for sure? Do you know what 4 will be transformed to? Is 4 here? No, we don't know that because it depends on other numbers. The only thing we know for sure is that minus 47 will be changed to 1. Then because minus 21 minus 21 is in the same column, it's the second, so it will get 2. Even though minus 21 is a very small value, it will not be changed to 1. Minus 19 and 19, though, will be, because they don't collide with something smaller. One way you can look at this is for every value, if it's smallest in row and column, then change it to 1. Or another way to think about it is handle numbers increasingly by value. And this second idea is easier to realize because we know how to sort elements. Sorting will be fine. Sorting speed is fine because that's n times m, size of the grid, multiplied by logarithm of the number of numbers. That's logarithm of the product as well. Still, it's logarithm. Logarithm of almost whatever you put here inside is very small. Even if you put here times n times m times m, it's still only logarithm, and that's very fast. By the way, logarithm of product is the sum of logarithms. So this is the same in terms of constant factor, in terms of time complexity as this. You can drop the product of repeated values. Indeed, we will iterate cells in sorted order. For that, I will first say, I will grab some tuples like array of ij, comma I, comma j, I don't know, tuples, pushback or something. This is pseudocode right now. This is our first double for loop. We grab all the elements and then we sort tuples. Sort tuples. And that's the time complexity. Linear of size of the grid multiplied by logarithm. And now in this order we can apply the idea that every time when we look at some cell, we want to know what small values were already used in this row and in this column. See an example. Uh, there is this matrix here on the left. Let's try to solve it. While you solve such a problem, if it's obvious to you already what is the solution, you don't really need to analyze such a big example, but it might help if you're not sure about the code. Okay, first we consider minus 47, that's the smallest. We look at this cell. We grab maximum out of row, maximum out of column. Both don't exist, so let's say that maximum is 0 so far. And we need to go this plus 1. That's 1. Then goes minus 21. This is second smallest number. It's this one in top row. So this thing. Maximum in row is still 0, but maximum in column is 1. So I need to be 2. I cannot put 1 here because 1 was already used. And I'm something greater. So cannot be done. Then minus 19. So far I claim that x is always maximum in row, maximized, how do I type this? Maximized with, let's say in row, maximized with whatever is maximum in column, plus 1. If I just do it like this, it breaks when I consider minus 19s, which shows that this is a good example. Because for first minus 19, let's say you consider this one first, the maximum in row and column is both 0, so we can put here 1, and indeed, 1 is a correct value to put in second cell of first column. But then if you look at another minus 19, using this formula, you will think that here you cannot put 1 because you already did it in the same column, so you will put 2 here. And that's incorrect. We need to detect that both minus 19s are equal. We need to detect ties. Ties actually shouldn't trigger that one is greater than another. They should be equal. We should put here 1. Then the next number to consider is what? 4 and 4. Both of them should be 3. It's not that one is 3, the other 4. Like this, then goes plus 19 here and there, and so on. This is what you get so far after considering numbers on the left from minus 21 to plus 19. Then the next one to consider would be 20. Oh, I skipped 14. I skipped 14. So 14 is, I believe, 3. For 14, max in column is 0, max in row is 2. So out of those 2 is worse, plus 1, 3. And we don't even need to think about it as this kind of formula. Just if you know already that you use those values that we see here, what can we put here? Well, 14 is greater than minus 21 in the same row, so 14 needs to be transformed into a number that is greater than minus 21. So the number 3. Probably for now skip duplicates and then correct them. Yeah, but duplicates still affect future values. At least one duplicate you need to handle. If you skip, let's say this is the situation. If you skip this duplicate because this is another 4 in the same column, you will mess up if the next number to consider is this one on the right. Right now, if question mark is not filled, you will put here 2. But actually what should happen is you should have put 4 here, no, sorry, 3, because that's a tie with second row. And then there on the right only goes 4 if it's greater than 3. So you cannot completely skip duplicates. We should process all elements with one value together. That's some way to do it, yeah. We can, when we go through the sorted sequence of tuples, the one we gathered below, then as we go through it, when we look at first value 19, maybe we should at the same time do something for all values 19. That's one way for that, and only then really apply them. So let's see what happens before we consider force. This is empty. This empty, this empty. Cool. We have this grid and we need to consider both force. The force that is here and force is there. We need to do them kind of simultaneously. How can we do it? For each of them, we can decide what it should be changed to, but maybe it's good not to yet put it in the grid. When we consider now multiple force, I will do the following. For every like, tuple of form 4, comma, some row, comma, some column, remember what it translates to, or transforms to, and do not modify the grid. I want the grid to still be like this. So when you look at this 4, you will in some way remember that 3 should be here, but you will not put 3 here in the grid. You will just remember it, put it aside, this information. Then when you consider another 4, and you want to put it here, you will use still the old max, the one from before another 4, because another 4 shouldn't affect my value. Some way to implement that is the following. Remember what it transforms to. Actually, for now, I think we should talk about the exact implementation event without ties, because depending on that, a fix might be different. Let me read the chat. Where am I at? My family town, so family house. Managing memory. I don't know. Usually memory is not an issue. It's actually rare that your program is fast enough, but it uses too much memory. Summer internship offer. You're welcome. I'm happy that my streams helped. Keep indices for each row and column. I didn't get that suggestion this team. So I'm not sure what that is. What complexity I am aiming for? I want to get around this nm multiplied by logarithm. The constraints are here, 500, as I said at the beginning. In code forces, it would mean that cubic is okay, 500 cubic. In lead code, no, the limits are also adjusted to slower languages like Python, so we want to get something faster than cubic. It can be 500 squared times logarithm. So most likely n times log of something, whatever that something will be. What do we do to find maximum in the row and column fast? For now, we leave aside the issue of ties. Let's assume that in the input there are no ties. The slow version is for every new cell, we can iterate through a row and get maximum. We can iterate through a column and find maximum. But, as you might guess, there is an easier way. Tell me, chat, what's the easier way? For each row, keep indices of cells for each values. Keep indices of cells for each values. But it is not true, just in case you want to assume that, it is not true that in the same column, all same values will transform into same. Oh, actually, it is true. Oh, I see. That's actually more tricky than I thought. Huh. I found a mistake in my reasoning. I wanted to say, I described this to you, a way to deal with ties, that for every number separately, every equal number, this was equal to that. For each of them, we find the maximum in the same row and column. For this one, it is 2 in the same column. For this one, it's also 2. So both of them get transformed to 3. But it's not that one should trigger the other to be 4. But if there was already 3 here, Then when you look at this question mark, you will try to replace it with 3. You will not do it yet, you will remember it. Then this other question mark, you will want to replace with 4, so you save that information. And then finally you will put both values, and you have 3, 4. But that's wrong. The statement said two values in the same column, if they were equal, they need to be equal. So, because this second question mark, both of them were initially equal, second question mark, it needs to be at least 4, so you put 4 in both places, which is trickier than I thought. I think we need to find some kind of connected component, some kind of group of equal values that they for sure need to be all equal. And for all of them at the same time, we'll find a max in row and max in column. I see how this problem gets so much harder because of ties. In such a case, I would say the problem should be split into two versions. One of them is without ties and one is with ties allowed, because that would be a follow-up in a real interview. First, you would solve a problem without ties, that's easier, and then they introduce this new thing if you have enough time during an interview. I'm reading the chat. Yes, Gupta, doing it together is better than updating one by one, because when you update the first of them, you might not realize some other requirements. Some other element will be actually popped up to 5, and you used too small value for the previous element, and all of those need to be equal. Mm. How is memory used and how to estimate the complexity of the algorithm? I think there are plenty of articles and videos for that. Time complexity and space complexity are very common. Space complexity is easy to calculate. It's just what kind of arrays you use. It's harder if you use memoization, but still, your memoization, if you replace this with an array, how big the array would be. Mm. Can I use captions on YouTube? Uh, you should use English if you're able to use English in the chat. Regarding captions in YouTube, I add them whenever possible, so whenever I'm able to. Two vectors for that. I don't know why you want vectors. I would use arrays. Enum's not good to use. Enums is just technique of implementation. That's something. For now, we talk about an algorithm, something not really dependent on a language. And enums are okay. Oh, did we figure out? We did not talk about anything better than just iterating through the whole row and column, but for now we don't have a correct solution. Doesn't matter with what speed, we do not have a correct solution. Time is for time, space is for memory. That's the difference. No. New slow algorithm. For every tuple, and this remember what it transforms to. No, we need to find, I think, connected components. So those, if you have value 4 initially, like here, there is value 4 in intersection of second row, second column, and also fourth row, second column. They are in the same column, so they are in some way connected. They need to be handled at the same time. But if there was another 4 in top left corner, it would be separate and wouldn't need to be equal to other values. How do I do that? Oh, I think that's very annoying. I need some kind of DFS for that. Chat, do you see an easy way? I can describe what I would use, but I hope there is something easier. So the question is how to find a group of cells that should be all equal. So those elements are equal initially, and they are in the same row, in the same column, maybe not all directly. An example of that would be some matrix Let's expand it. If there is initially 7 here, 7, no, 7, 7, and like this. Those 7s are all connected in some graph way, in graph interpretation of that. Like those two 7s, they are in the same column, so they are connected with, let's say, an edge. There is an edge here between those 7s, an edge here, and so on. I don't see. It seems lead code isn't that easy in the end. That's right. It's relatively easy, okay? It's relatively easy. And I don't claim that this is, compared to code forces, this is still very easy to figure out. And my question to you is, how can we do it easier than what I will describe? So, indeed. But I can change my stream name to lead code is relatively easy, but I don't think it's that catchy. Union find. The biggest issue here is how to find edges. Then the way to find connected components is a detail. I think I will use DFS. I will use some kind of DFS. For every row, store all occurrences of every value. For that, I will have map from int to positions, where in column and where in row. From int. And I do that where in row for everything. Let's say h is height of the grid. Height width. I hate using n and m because it's not obvious which one is which. I will even say that matrix length. This problem uses the swapped values. Normally you say that there are n rows and m columns, and I did it the other way around. Okay. We use this. Now definition, where in row of 7 stores position of 7 is just this, is a map. It's a map. Where in row of 7 of, let's say, 0, 7, this is a list of occurrences of value 7 in row 0. Describing row 0. Okay, that's the definition. Whenever I use where in row of I, that's information about row I. When I use this, then from this particular map, I grab a vector for key 7. And the value of this in the map is the list of all occurrences. Those occurrences are just columns. So in this row, I know 7 is here, here, there. BFS on unique values. Any graph searching technique can work. I also thought about BFS at the very beginning. We will get back to this. I'm not 100% sure if this will be better. But I will go with this. And now, to find connected components. Let's do that. So for tuple in sorted tuples, this is of course some kind of pseudocode. Let's untie. So let's say for tuple value, comma row, comma column. Sorted tuples is the list of all cells sorted by value and also if it's row and column. If not, I will visit it of row column because some of them we already visited. We already know what values we put there. Then we want to find the connected component including this value. Like, okay, if in this grid of mine, if I run this for the 7, I want to find all other 7s. Oh, this one, this one, this one. Because all of them I will want to replace with a single value, with the same value. So here, find connected component, CC, with this cell. I will call it, I think, DFS. You can do BFS if you want. So here, whatever, for finding connected component. That's the easy step. DFS of row column, and it will do the following. There is earlier subtraction. DFS of row column. For, we know that what is the value here. This is the, how is the value called? A matrix. Matrix of row column. Now, for every column in this, where in row of this row it describes a map, everything about this row, and I want this particular value x. So for all positions of the same value in this row, if not visited yet, if not visited of row call, call is bad name, let's call it C2, new column. If not visited, then DFS of row C2. And you do the same for, this was in this row, you do the same for a column. For every row in this column with the same value x, if not visited yet, DFS of R2 column. Sorry for not being consistent with the style of counting. Like that, at the beginning of DFS, visited is true. And we can gather those cells in some way, let's say connected component pushback a pair row column. This might be some kind of vector of pairs. What is this spam in the chat? Okay, let's say timeout first. But I'm timing you out and not banning only because I hope that your internet connection got laggy or something. So there is something here that we could pass by reference or we could make it global. Now this is how I found this whole connected component. Like I found positions of all those sevens that are connected. Then, not visited, I ran DFS, found the connected component, and now new value, initially let's say is 0 or something. For every cell in the connected component, I need to maximize it, the new value, with what? With maximum in this row and maximum in this column. Max in row, max in column. Do you see all of that? Yeah. He was Eric Cole. Stupid nickname, right? You can't even pronounce it. Like that, and then we iterate again. Notice that there are two separate for loops, and for every such cell in this connected component, the value there. Can I just overwrite matrix? I think I can. Yeah, I think I can. Or just in case, let's say new matrix of this cell. This cell is equal the new value plus 1. Done. Why two separate for loops? It's not that as you go through one, you already know for every cell what it will be replaced with. Only once you get maximum out of all of them, then you know what to put in all of them. I explained that. Where did I explain it? Here. If there was a 3 here and both question marks were the same value, bigger than everything so far, then here you would try to put 3 and you would try to put here a 4. But actually, because they need to be the same, 4 should be there as well. So first go through all those question marks that are connected in some way, like here all those sevens. For sevens meaning initial value 7. For each of them in this row, in this column, you want to know max so far, and you get the worst out of all of those requirements. What rating would this problem be? I never know how to answer that because when I learned algorithms, there was no such thing as problem rating. It was division 1 A, B, C, D, E, stuff like that. For division 1 A, this problem would be a thing of proper difficulty but too standard. Maybe I think between division 1A and B, I think it would be better for an educational round because it is a very educational problem. How do we get max in row, max in column? Without iterating through the full row, full column. Because the total number of cells for which we want to consider and we want to compute the answer is of course quadratic. The full grid is quadratic, n times n. Instead, we want to do this in constant time if possible. If possible, we want to just read it from an array. Oops, max in row, let's say max r for this cell dot first. Max c in cell dot second. If cell was a pair, so this corresponds to row, this corresponds to column. Can we do that? So can we maintain such arrays? Yes, we can, and this is actually quite easy. Initially, we'll create them both filled with zeros, max r of size height, filled with zeros. Same with max c of size width. Of course, you can use vector if you want. And whenever you put some value like that, you just update value in row and value in column. So here, when, let's see an example. When you already know some values, I don't want to put values everywhere, but let's say in first row the maximum value is 0, here the maximum value is 2, here it's 1, here it's 1. And regarding columns, it's 2, 2, 1, the maximum. And now, because maybe like here there is 1, here there is 2, all that kind of stuff. And this was so far empty, and now you put here a 3. What happens then? You just update the maximum in this column, in this row to be 3, and in this column to be 3. So you maximize this. Max r of cell first is maximum of itself. I should now just repeat this term, comma, new value plus 1. ABC has 8 problems. That's quite a lot. If they have enough problems, then I guess why not? But even more, I wouldn't want to participate because I would need to go through so many problems. That's it. We're done with, of course, not the actual code, pseudocode, but I will summarize what we did. First, we get all the cells and we sort them by value. For that, I have triples, value, index, index, value, row, column. We sorted. Then we create this kind of complicated map so that for in every row, let's say in row 0, for value 7, I would know where is 7, all the occurrences. I would have such a vector list of occurrences. And oh, I know one more issue. I think that's right now it's still cubic. I will explain that later. So we create that. Also, in every row and every column, we keep maximum out of values we already chose. This new matrix that we create. Initially, everything is 0. And in order of sorted cells from smallest to biggest, if something wasn't yet decided, then we run DFS. So it's like, if this is a new value, such that it's not that we already considered an equal value and it was in the same row and column, row or column as this one. So if this is a new value, we DFS for it to find all the equal values that are directly or not connected, like this set of all sevens. We would know their positions. We would then, for all of them, see what's the maximum in the row and column. We would get maximum out of all of those, and then this value plus 1 we would assign everywhere. Also updating maximum in row and maximum in column. This is almost quadratic. There is one step that makes this cubic. Tell me why. In particular, I'm quite sure that everything here is okay. I will mark this. This part is fine. Every cell here will be only once considered. This is not an issue. Six problems ABCs are pretty unbalanced. I don't know, I don't participate much. F is indeed quite difficult. So chat, do you see why actually what you already see currently on the screen, it's quadratic? And how to fix it, that's maybe even trickier. And because I told you that what I marked is not an issue, then what was left on the screen was DFS. This DFS makes everything cubic. For every cell, it is linear, because for every cell will be handled once. For every cell, it iterates over this and that. If there are a lot of equal values in the same row or column, or both, this is linear per cell. In particular, the worst case for my current algorithm is a matrix with all equal values. Because for every cell, you would iterate over everything in this column and in this row. That's pretty bad. For every cell linear means that it's cubic in total. DFS is quadratic. That's not a way to say it. For every cell, it's linear. The number of cells is already quadratic. So it's height times width. And now for every cell, and there were that many of them, you have h plus w, height plus width. This is the number of cells in the same row plus column. We would need to quickly, in a column or in a row, find equal values. And here's a magical fix. This is one of those moments where you can struggle, you can think about some hack and eventually get accepted, but also maybe somebody can tell you that there is a very easy way to handle that. We can, once we go through a vector, we can clear it, which sounds crazy. It will not exactly be like this. It almost works, what I will tell. After you iterate over a vector, where in row of row x clear, you get rid of all elements of this vector. DSU, I think, yeah, the DSU would also be fine to find connected components. You would have similar issues of how to make this work. Yeah, DSU would be indeed better. Because, already here, when you would find all equal values in the same row or column, you would merge them, so you would union them. But I will fix this by saying that, and same for column, column, column. Now, why I hope that this works? Because in every row, it's bad if for every cell you iterate over this row. Then it's in total, every cell is linear, that's bad. But if in every row only one cell is able to get through all of those elements, that's okay. So there are maybe 1,000 equal elements in a row, but only for one of them you will iterate all 1,000. For the others, you will not. But if you first run the FSs and only then clear, that's bad because you went deeper here in the FS, and those already started maybe iterating through the vector. Actually, we need a smarter hack. We need TMP to be this vector, then clear it, so every other DFS call would already see an empty vector, and then iterate over TMP. This is a very hacky, but still quite easy fix. And you do the same for columns. So again, you do TMP the TMP is equal this thing for column, then you iterate over TMP, and here this thing with column you clear, like that. Your homework here after the stream is to think more about this ugly hack. But formatting, I guess. I'm reading the chat. Yes, I am in a different place. Am I using Python or C++? I'm using pseudocode. So it was ugly combination of Python and C++. This code is a very ugly creature. Sorry about that. It's not that important that I present to you the full code. It's important that I describe the algorithm. And also, I used to do more of just talking about algorithm. Now, almost always I at least list down steps or just do pseudocode. What we created here is most of the code needed. And that's it. This is the end of. Oh, I need to sign in, so I will not do that. Um, this, if you want, I can paste all of that if you ever want to use it. This is, let's say, C++ mostly. Create new, and this is final code. I will not explain this today. You don't like those functions? Uh, that's a strange. I never heard somebody disliking, for example, clearing the vector. Fine, you do you. That's it for today. I don't have time for other problems. I think we discussed this one in detail. I hope after today you understand coordinate compression and also this much more difficult problem. Let me know maybe in YouTube comments if there are easier solutions for this. This is one of the last streams in the next weeks because in 1 week from now I'm starting a 2 week break. So in middle of August there will be no streams, but still there will be one on Tuesday. So see you then. Bye guys. Just one last look at the chat. Classic. No, but